easy. This is not a hard homework. But not this time. This time the theory is still easy because there's only basically one formula. Okay, we're on the air. So last time I was talking about homework 3, and so the question is, are there any questions about that? No? I thought there were some questions. Yes? No, actually there is no hard part. This is an easy homework. Probably the hard part, which really has nothing to do with the course, is writing the simulation. All you have to do, though, which I explained last time, was you get rid of some instructions, the ones that compute the fraction of time you're in the blocking state, because we know that's going to be the same as the number of customers, now fraction of customers, who find the blocking state because of the Pasta theorem, so there's no need to verify it again. And so then the question is, how do you incorporate the Q into the model of homework 1 where there was no Q? And that's what I showed you last time, or I gave you the outline for it. I didn't give you the actual code. Now here's what it asks you to do. You've got this table, and there's 4 cases. So you're going to do it for 2 different input cases. One is where the lambda, or the arrival rate, is 4 customers per second, and the other where it's 4.2. And in our case, let's see, we know that the offered load is equal to the arrival rate times the average service time. And in our case, tau is equal to 2.4 seconds. So in this first case, this means that lambda is 4, lambda is 4. And tau was it 4.2, was it? Is that right? Okay, what do we have here? 2.4. 2.4. So this comes out to be 9.6 erlangs. Now I asked you to measure take the units of time to be the average service time, which means that you would divide by 2.4 to make tau be 1, and then you would multiply the arrival rate by 2.4 to compensate for that. So of course you still have the same 9.6 erlangs. And for that it asks you to calculate some stuff. It asks you to calculate the utilization, the average value of the waiting time, and the complementary waiting time distribution function. Probability waiting time is greater than 0, probability waiting time is greater than 1, and so on down to the probability that the waiting time is greater than 8. And so this value here, this would be measured in units of average service time. This is the fraction of customers who wait more than 0, that is, who wait in the queue. This is the fraction of customers who wait more than 1 service time, so it's more than 2.4 seconds, and so forth. And you want to do this for various cases. So there's case 1, and you have theory and simulation. Now, there's also, you're going to repeat this for the case in which the lambda, instead of being 4, is 4.2. And that apparently small change makes a big difference, because if lambda is 4.2, then the number of erlangs is greater than 10, and we have 10 servers here. So in the second case, you don't have convergence. So there the answers are sort of common sense, because that's the case where the queue length in principle builds to infinity. But I want you to see when you actually run the simulation how the values work. Okay, there are going to be now 4 different cases for each lambda, which correspond to the same cases that you had in homework number 1, namely Poisson input exponential service times, then Poisson input constant service times, constant input exponential service times, and then constant. And the exponential case is the one that nominally is handled by the rate up equals rate down equations. But in the case in which there's insensitivity, the results apply sometimes, even when the exponential distribution is not required, is not involved. And let's see. The third case, the fourth case, which is the one where you have constant, that's not really a standard queuing model because there's no randomness in it, but nevertheless, in some cases, it's worthwhile looking at. So we compared those. Now, one of the reasons I chose the constant as the other distribution to compare against the exponential is, first of all, the constant is easy, and second of all, in some sense, the constant is the farthest away from the exponential of all other distributions. So it makes for the most extreme comparison. And the reason it's the farthest away in these terms. If you ask what memory the distribution has, the exponential distribution, remember, has no memory, meaning that if you have an exponential variable, no matter how much time has elapsed, if the lifetime is still alive, the future lifetime is independent of the elapsed lifetime. So there's no memory. On the other hand, if the random variable is deterministic, then it's the extreme opposite, which is it has perfect memory. So for example, if the average service time is 10 minutes and 8 minutes have elapsed, then the remaining service time is exactly 2 minutes. So those two are opposite ends of the spectrum from the point of view of memory, so therefore it makes for good comparisons. So we're going to look at these four cases, 1, 2, 3, 4. So let me, instead of writing 1, let me write it this way. In terms of the standard queuing terminology, this model is M/M/S. That means Markov or memoryless input, which means exponential interarrival times or Poisson input. This means Markov, again, service times or exponential service times. That means S servers. In our case, S is 10. And it's implied in that notation that there's an infinite capacity waiting room. Okay. Now, the second model was where the service times are constant. So in the standard queuing terminology, this would be the model MDS. The D stands for deterministic. And again, you have theory and you have simulation. Then the model where you have constant interarrival times and exponential service times, that would be DMS, theory, simulation. And then there's the case of constant. So if you were using the standard terminology, that would be DDS, no randomness. Theory, simulation. Now, one reason that I'm writing down these names is that, well, it's standard notation, so it's something you should know. And the second thing is that these are classical models, so these are out there. They're in the web, on the web someplace. You can find some of these, and so you could then make these calculations using one of those calculators. If you can find it, that's fine. But for this case, this is what I developed the theory for. I want you to make the calculations using the formulas I gave you. So if you can find a calculator on the web that does it, well, it should give you exactly the same answers. But I don't want to just see the answers. I want to see the formula that you used. In future homeworks, the same thing will be true, but the calculation will be more difficult. And so just looking things up on a website is not worth very much. So I want to, if you can find these things, some you can, some you can't, I'm not sure what's out there, then that's fine. You can use that for your own benefit. But if you're asked to make a calculation, then you have to make the calculation using the theory that's presented in class. Yes? No, the theory we developed, well, it depends on which thing you're calculating. So we calculated several things. First of all, we said that rho, that's the utilization. By definition, that's the carried load divided by the number of servers. By Little's theorem, we argued that that's the same thing as the offered load divided by the number of servers. And this should be true whether or not, that is by Little's theorem, this result is true regardless of the distributions involved. So this measure is insensitive to the distributions. So in our particular case, we have 9.6 Erlangs, we have 10 servers, so our utilization is 96%, and that would be true for all of these. So you could write either 0.96 or 96%. So the utilization measure then is totally insensitive to the underlying distributions. So that's worth noting. And when you run the simulations, you'll see that they all give 90% utilization. And since they give different answers for the other things, that shows that the utilization by itself doesn't really tell you very much about the performance of the system. Okay, so these will all be 96%. In the second case, in principle, where the offered load is greater than a number of servers, greater than 10, then the utilization in theory would be 100%. And when you run the simulation, you'll find that, well, of course, there's a contrast between the two cases. In the case where the offered load is less than a number of servers, so that you have convergence, you have an equilibrium distribution, then the longer you run the simulation, the more tightly the simulation results should converge, should cluster around the theoretical final value. In principle, it should be exactly the same as the theoretical value. On the other hand, when the arrival rate is, when the offered load is greater than the number of servers, then the theory predicts that there won't be a statistical equilibrium solution, and the queue length will be infinity, and the average waiting time will be infinity, and the utilization will be 100%. But of course, when you run the simulation, you can't get numbers like infinity. If you calculate the average waiting time, what you see is that as the length of the simulation run grows longer, the average waiting time measurement that the simulation produces will grow larger, and it'll grow linearly with the number of customers that you generate. But of course, it'll never be infinite unless you run your simulation for an infinite length of time. So in the first case, you'll see that everything settles down and stabilizes, and in the second case, you'll see that everything, nothing stabilizes, or, well, I shouldn't say that. The utilization will stabilize toward 1. But essentially what happens is that the things like the waiting time and the queue length, they just keep getting bigger and bigger until they don't settle out. There's no equilibrium distribution. Okay, so that's one of the things that this is going to illustrate. Now, what about the expected value of the waiting time? So we have a formula which we derived. Let's see if I remember it properly. It's the Erlang C value. In our case, S is 10 and A is 9.6 in case number 1, divided by 1 minus rho. Rho is 96% in our case. S, and then here we have tau. Of course, what I'm asking you to do is to calculate the expected value of the waiting time in units of average service time, which means effectively that you're going to call tau equal 1, and what you're going to have is the average waiting time in units of average service time. So when you run the simulation, the way it was written for homework number 1, everything was written in terms of seconds. So you can keep the simulation as it is, and then when you get to the end, change the answers that relate to time from seconds into service times. The other possibility is that you can change the values of the parameters in the simulation run from seconds to service times right at the beginning, and then the answer will turn out to be in terms of service times. So that's your choice. But it's important to note that the conventional way of handling these things is you have to pick some kind of unit of measurement. So typically, the unit of measurement you pick is the average service time. So you're setting the average service time to 1, you're readjusting the arrival rate so that the offered load is the same, and then you go from there. Okay, so this is a formula, and the way you calculate the Erlang C is with the algorithm that I gave you, which is that you calculate the Erlang B using that iterative scheme, and then you go from Erlang B to Erlang C. There was one step that relates the Erlang B to the Erlang C. I gave that in class. People remember that? That's in chapter 3. Let's see. If I can find it. Okay, birth and death queuing models. Okay, the iterative scheme for calculating Erlang B is on page 82, exercise 6. And there, the exercise just asks you to prove that it's true. The proof, of course, is just algebra, and it's in the solutions manual. My point here is to use it. And then the relationship between Erlang B and Erlang C is given by exercise 16A on page 92. So you calculate the Erlang B using this iterative scheme. Then you use the formula that gives you the Erlang C in terms of the Erlang B. Okay, so that's how you calculate this. Then it asks you to calculate the probability of W greater than T for each value of T as listed. And we derived in class that if we have Poisson input, exponential service times, and FIFO. Remember, this formula does not require FIFO. That was one of the conclusions that we drew from Little's theorem, that this is valid whether I have FIFO, LIFO, random order of service, whatever, it doesn't matter. But here, the requirement is that we have FIFO service, first come, first serve, first in, first out. And the formula is the Erlang C value times e to the minus 1 minus rho s mu t. Of course, mu is the reciprocal of the average service time. So in our case, we take mu is equal to 1, and the t is then measured in units of average service time rather than in terms of seconds. But this was the formula that I derived in class. So you use this formula to calculate these values. But this assumes, now, these formulas assume below this line, assume that I have M, M, S. And this formula assumes FIFO. Okay, so these calculations are simple because there are the formulas. There's nothing to it. Now, you're supposed to plot these things. So what's the plot going to look like? It asks you to plot it for the case of the case number 1, the MMS. So here is the probability of weighting greater than t, and here's t. Here's 0. So the graph would look like this. This value here is the probability of weighting greater than 0, which of course is exactly the Erlang C value. And then, if you plot this curve, you would get something that looks like that. Now, then it asks you to, on the plot of the theory, to put down the values the simulation gives you. So here is 0, here's 1, here's 2, here's 3, here's 4, and so forth. So when you run the simulation, you're going to measure the fraction of customers who had to wait on the queue, and you put that value here, whatever it turns out to be. It should be very close, of course, to the curve. Then this is the fraction of customers who had to wait more than one service time, or more than 2.4 seconds. So the simulation maybe gives you a value here, and then you get a value here, and so forth, like that. You're not supposed to connect those points because the purpose is not to interpolate. The purpose is to see how well the theory and the simulation agree. And in principle, of course, the simulation value should lie right on the curve. If you do it right, they'll be so close you can practically hardly tell the difference. Now, when you do it for the MDS, these formulas don't apply anymore. This formula applies. It applies in every case. But this and this assume that I have exponential service times. So, therefore, you can't calculate the theory for this column. So what I said that you're supposed to do is if you can't calculate it, then write NA for not applicable. So you don't know what the answer is. Now, you might be able to find the answers on the web. If you can, then fine, write them in there, but tell me where you got them from. But the calculation, the mathematics behind this is much more complicated in the case of deterministic service times than it is in case of exponential service times. And that's something that always seems surprising to people, is that the case of constant anything is more difficult than the case in which you replace the constant by an exponential. That is, why should the exponential be simpler? And the answer is, well, because it has no memory. Okay, now, if you then take your simulation results and you plot them on this graph, that's what's asked, then you'll get something like this. Now you're only going to plot the points because you don't have the theory. So you're going to get values, and it'll turn out that those values are going to be different from the values. It's clear that they're going to be different from the values that you would get when the service times are exponential. So here, this is an illustration of the fact that although the Erlang loss model is insensitive to the distribution of service times, the Erlang delay model is not. This will show it to you because the values that you get from the simulation will not be the same as the values you get from these formulas, which assume that you have exponential service times. So this will give you an example of how much difference there is, at least in this case. Of course, once you get the simulation written, remember, you don't have to stick, for your own benefit, you don't have to stick to the values I gave you. This is like a resource, so you can always run the thing for different values, different number of servers, different offered loads, compare it with simulation. In the simulation, you can put in any service time distributions, any inter-arrival time distributions you want, so you can play with it and see exactly how important and how sensitive it is to these measures. For example, if I ran the same program but with a much smaller utilization, then you would see that the agreement between the simulation results for constant service times and the simulation results for exponential service times are much closer. And in fact, they would converge to each other in the end as the offered load goes to 0. Because as the offered load gets smaller, the fraction of customers who wait in the queue is smaller, which means that you're in the queuing state less often. And if there is no queue allowed, then you know that the service times don't matter. So if you allow a queue but don't use it, you would expect that there would be less and less difference the less you use the queue. So these are insights that you get from doing these things. Okay, so this stuff right here, you know how to do this. You calculate these things, you put them in there, you do the simulation stuff, and it better be pretty close. Over here, this value is 96%. The simulation result should be close to that. You don't know what these are, and the simulation values will be something which you get by simulation. Okay, same thing here. The utilization is 96%, but you don't know what the theory for all the other things is, so you write NA, or get it from a website someplace. The simulation doesn't care what these distributions are. The logic is the same. So again, you'll see that when you run it for constant inter-arrival times, that you won't get the same answer as you got for exponential inter-arrival times. Now this one's a little bit different because, for one thing, this isn't a stochastic model. There's no randomness in it. But we already saw that in the Erlang loss model in homework number 1, where I asked you to do the same thing. And it turns out that, as the Little's theorem predicts, that the utilization will be 96%. But what about the other things? What's going to be the average waiting time here? Now, you don't have direct theory for that, but you have common sense theory, which is theory as long as you can explain it. Does anybody know what the average waiting time is going to be? Yeah, not about 0, exactly 0. All right, the reason it's 0 is you've already run this case. You've already examined this case in homework 1 where no queuing was allowed. And you found that the fraction of time that you were in the blocking state in that case, when there was no waiting room provided, was about 60%. And the fraction of customers blocked was 0. No one is ever blocked in that system. Well, if no one was ever blocked in that system, then if I add a queue, which would give the blocked customers someplace to go, whether it's there or not is irrelevant because nobody ever wants to go there. So since no blocking would ever occur, the waiting time would be 0 because nobody ever waits. So the simulation should show that this is 0. And of course, these two cases have exactly the same utilization of the servers, but they have wildly different values for the average waiting time, because that's 0, and that's a zillion times bigger than 0, as is any number that's not 0 itself. Okay, what about the probability of waiting greater than 0? Well, the same thing. Nobody ever waits. So these values should all be 0 in theory, And of course, the simulation will show that. Okay, so this is simple. This is straightforward. So let's make it do a week from today. I can see some grimacing out there, but this is an easy problem. And in fact, all of these problems are sort of easy if you keep up, because they're just minor changes from one model to the next. So in this case, but this is easy. There's the theory. The simulation is minor if you know how to write a program, and that's all there is to it. Any questions about this? Okay, so now I want to go and look at the next model. I think I've covered everything I want to on this. Yeah, here is the homework 1, and what I did was I wrote out here how to change directly from homework 1 to homework 3. I eliminated a couple of instructions because I don't care anymore about the fraction of time you're in the blocking state. And then I added some instructions to account for the queue. And they're about the same number of instructions, so the total length of the program is about the same. So it's no big deal. Of course, if you don't get those instructions right, it's a big deal. But I mean, it's not complicated. So if you understood how to do homework 1, and if you understood the argument that I gave you for the simulation diagram I put on the board last time, this should be a straightforward exercise. Okay, so now I want to go to the next model. And this model, I think, is underappreciated. So I'm going to try and make that argument. The model that I'm going to do now, the model that I just did, that's covered in the Bertzekis and Gallagher book, so you should look that up. Remember, you should be reading Chapter 3 now. And Chapter 3 has little theorem worked out in some detail, and then he has some other stuff with, I think, less detail, at least at the beginning, and less insight, more a matter of giving formulas than what's given here. But you should check this out, and at the same time that he discusses these models, he also gives examples of how they're used in analysis of data networks, because that's what his book is about. And so I'd like you to read that, because that puts this stuff in context, and that's the reason for teaching this course in a computer science and engineering department as opposed to in a mathematics department or operations research, something like that. So the model I want to use now is what's called quasi-random input. It's in section 3.5. And this is not in the Bertzekis and Gallagher book. .5 quasi-random. Not a really very good name. But the reason for the name is this. A lot of the terminology comes out, or some of it anyhow, I say a lot, certainly a lot that I use, comes out of the teletraffic engineering or teletraffic theory community. Because remember, the original motivation for developing queuing theory was for the analysis of telecommunication systems. And up until the 50s, maybe, before computers, that was the primary application. And then when computer science and engineering came along, then there was sort of a rebirth in the subject because of the applications in computing. Also, there are a lot of other applications, but those applications tend to be the important ones because they're the more technological ones. So you can have major companies working on specific kinds of contexts or applications, and so expertise grows up in those areas. So originally, the essential assumption that was made for arrival processes in the telecommunications area was Poisson arrivals. And originally the terminology that was used was that Poisson input was sometimes called random input. And then when they had inputs that were not Poisson, like overflow traffic, we've already discussed that, that was often called non-random input. course, that doesn't really make any sense when you think about the words, because overflow traffic is random, but it's not Poisson. But in any event, people tended to use the words Poisson and random interchangeably. And when they got to this model that we're just going to discuss now, this is sort of Poisson. So it really should have been called semi-Poisson or quasi-Poisson, but instead it was called quasi-random. And this terminology has stuck somewhat in the telecommunications, teletraffic area, but not outside. When I wrote this queuing book, at that time, I learned all this stuff in the context of teletraffic engineering, teletraffic theory. I was at Bell Labs, and that's what they did. That's what my group did anyhow. And so I used all of the telecommunications terminology. And this had an advantage and a disadvantage, because at that time, queuing theory was a subject that was just beginning to become popular and useful outside of the teletraffic area. And that meant, on the one hand, that new terminology and new models were introduced, but it also meant, on the other hand, that there was a lot of stuff known that the computer science people didn't know about. And a lot of the telecommunication stuff was not published in the open literature, because most of it was done in one company in the United States. In fact, in each country, there was a company like AT&T or NT&T or something like that that was the telephone company. It was a monopoly, and so they did their own research and they published in their own journals, and some of the stuff was secret because it was company confidential. So it took a while for this stuff to become more of an academic discipline. So that means that there were like different strands of development. So my particular background began with the teletraffic version. So some of the stuff in this book is a contribution to the field because it made work that had previously been unpublished in the teletraffic area available to everybody. On the other hand, it was also looked at as being too specialized because it was about telephones. Like, for example, there's a really excellent book that had a lot of influence in the development of queuing theory. It's called, unfortunately, it was called Introduction to Congestion Theory in Telephone Systems. Terrible title. I remember there used to be a commercial on television for some kind of nasal spray. It said, "These are the sounds of congestion," and then you would hear this terrible sniffling. And well, fortunately, they don't have that ad anymore. But to name a book Congestion Theory, that kind of sort of like the theory of running noses. So I think that that was an unfortunate title, but if you can find that book, if anybody's interested, I'll show you. It's really a classic mathematical, beautiful treatise on queuing theory and its applications to telecommunication systems. Okay, anyhow, we're talking about quasi-random input, which is sort of like Poisson input, but not exactly. Some critical differences. And here's the basic idea. Our rate up equals rate down equations, if you remember, looked like this. Let's see if we get something that writes. We said lambda j pj is equal to mu j plus 1 pj plus 1. And then for Poisson input, we said that the birth coefficient does not depend on the state of the system, and so we wrote lambda j is equal to lambda, and that made everything simpler because we didn't have a dependence on j. The mu j's, that's what specified the Q discipline, because if you remember that, for example, when blocked customers were cleared, all the mu's are 0 for states that correspond to more customers present than there are servers. For the case of blocked customers delayed, the second model we looked at, then we saw that we had two different forms for this aggregate service completion rate, depending on whether the state was one in which there was a queue or there was not a queue. So what we're going to do now is I'm going to change the assumption about the lambdas, but I'm going to keep the mu's the same. So we're going to look at the case where we have quasi-random input. And I want to give the physical meaning of this. So here's quasi-random input. And here the assumption is that the birth coefficient when you're in state J is equal to n minus j times gamma. N is the population size. So I'll say number of sources. And gamma is a parameter like lambda, but it relates to per source instead of overall. So now the idea is that we have a finite number of sources. So here are my sources, like that. And there are n of them. So we have n sources, and then we have some servers, just like before. Say s of them. And the sources request service. Question? It says lambda j is equal to n minus j times gamma. This is a Greek g. Gamma. And what I'm trying to model is the idea that there's a finite number of sources. In a telephone context, these might be telephone subscribers. They're just phones. They're sitting there, and there's some number of servers or trunks. I think these would be called lines, and these would be called trunks. And a line wants to be connected to a trunk. And when a line is connected to a trunk, that removes it from the calling population. So in the case of Poisson input, we saw that the probability of having an arrival in any interval of length h depends only on the length of the interval and the parameter value lambda, but it didn't depend on the past, it didn't depend on the future, didn't depend on how many customers were already present in the system. But now we're going to change that. Now we're going to say that when a customer makes a request for service and is being served, he's removed from the calling population. He can't make another request while he's being served. And therefore, the instantaneous request rate depends on the state of the system. And in the model, it depends on the state of the system linearly, in the sense that if I have n sources and I'm in state j, meaning j customers are in the system, that is, they're either using the servers or waiting for service, then the number of sources that are eligible to make a request for service is n minus j. And then the request rate, the instantaneous rate, is proportional to the number of sources that are eligible to make a request, and the gamma is a traffic parameter. Yes? Oh, well, no. Okay, the question is that when you enter the blocking state, then the arrival rate would go to 0 because there would be nobody else left. Well, that depends. We're going to look at two different queuing disciplines, just as we did before. Blocked customers cleared, blocked customers delayed. In the case in which the blocked customers are cleared, if a source makes a request for service and it finds all the servers busy, then it's cleared from the system, which means that it returns to its pre-request state just as if it had not made the request, and in effect is a retrial. On the other hand, if blocked customers wait in a queue, then when the customers are waiting in the queue, the rate goes down because customer waiting in the queue is not eligible to make another request, and the rate could go to 0. Of course, as soon as the customer finishes his service, then he would return to the state at which he's eligible to make a new request for service. So these systems are self-regulating. You never have to worry about convergence, for example, because if there's a finite number of sources, the highest state you can be in is equal to the number of sources. So it takes into account some kind of feedback, but what it means is that the offered load depends on the state of the system and cannot be specified in advance. So there's some complications added because of this, but there's actually theoretical simplifications because you don't have convergence problems anymore. So the essential mathematical problems, some of them disappear, but the calculation problems and the interpretation of what's going on, that actually becomes a little bit more difficult. Now, originally, this was for the analysis of telephone traffic in which we had lines and trunks. But now I have a paper which I'm going to discuss in which this is supposed to describe internet traffic. And the internet traffic imagines that you have a bunch of sources which go into phases of on, off, and when a source is off, that means in a sense he's idle, he's thinking, and then he goes on, that means he wants to make a request for service. And if the server is available, then he holds it, and if the server is not available, then in that particular model, he reverts to his previous state. And so you have these on-off switches, so to speak, which are competing with each other for a finite number of resources. And the claim in that paper is that this is actually a good model of traffic in the internet. And one of the interesting things about that is that people have claimed that if you measure internet traffic, it's not Poisson anymore, and therefore the old models don't work. Well, this is not Poisson, and the claim in this paper is that this actually does work. Whether or not it does, I don't know. I never actually took any data myself, but I'll show you the paper and references, and you can decide whether this is a good model or not. I think it's got a lot to recommend it, as we'll see. Okay, now, the idea here is that I'm going to imagine that each source has an exponential time until it makes a bid for service. So here's a source. Let's say it's idle. So there's going to be a length of time which is going to be exponentially distributed, and its parameter is gamma, so that the average time until it makes a request for service is 1 over gamma. And then it makes a request for service. Let's say for the sake of argument that we have sufficient servers, so then it becomes busy or ineligible to make a request for service for its service time. On average, that's tau. And then it becomes idle again, or eligible, or enters its think state, and so on. So what you have is you've got these guys doing like this. This is the on-off diagram. So that's off, on, and so forth. So we're going to assume initially that the on-off periods are exponentially distributed. And so gamma will be the parameter for the so-called think time, and tau will be the parameter for the service time. And sometimes this is called think time. Okay, so let me write that down, think time. And the reason for that is that in some of the early computer science models, this model was used to look at a case where the sources actually correspond to terminals. So there are terminals, and the terminals are sharing a bunch of computers or CPUs. And so these guys are sitting there at terminals, and then they request the use of a processor, and then they use the processor, and then when they're done processing, then they return to their prior state. So when they're sitting there at the terminal, they're thinking. So that's called the think time. And when they get done thinking, that means that they're programmers. This is interactive. So they're sitting there and they're thinking, and then they decide that they want to make a request. So they've been typing, and then they press enter. When they press enter, they're making a request for service. Now, if the processor is available, then they hold it for their processing time, and at the end of that time, they then re-enter their think state. And then they think, because the processor gives them their answer back. And then they think about it, and then they make another request for service. And so they have think time, processing time, think time, processing time. Now, in that model, it's assumed that when the processor is not available, that they wait in a queue. In our model, they return immediately to their think state. But that's the difference between block customers delayed and block customers cleared. So what I'm doing is exactly analogous to what we did before, but now instead of having Poisson input, we have quasi-random input. Yeah, question?
Just thinking that sounds a lot like a database system where you've got multiple servers all sharing a database, and they, with a thick client model, they do most of their computation here. When they need to get information, they reach over, grab it from the database, and then, like you said, enter that thing state.
Yeah, in fact, I think there are probably lots of situations that you could put in that framework. The important point here from our point of view is that you've got finite sources, finite resources, and the number of sources is more than the number of servers. And they compete against each other. If they're blocked, then just like before, we can assume that they wait in a queue or not. If not, then they return to their pre-request state. So that's sort of like feedback with retrials. And the difficulty, part of the difficulty is that the actual offered load, which is which relates to the arrival rate, that cannot be specified in advance of solving the problem, because if the blocked customers are cleared, then whenever a customer is blocked, he becomes eligible to make another request sooner than he otherwise would if he were served. So the actual offered load is higher than it would be if you provided more servers. On the other hand, if the blocked customers wait in a queue, then while they're waiting, the arrival process is depressed because they cannot make a request for service while they're waiting, and in that case the actual measured offered load is lower than what it would be if there were sufficient number of servers so that everybody got served. So these are issues that make the problem more difficult. However, as n goes to infinity, it turns out that the quasi-random input model converges to the Poisson input model. So what that means is that if the number of sources is much larger than the number of servers, then this effect doesn't matter. But if the number of sources and number of servers are relatively the same order of size, same order of magnitude, then it does matter. But I can't tell you when that is and when it isn't. I can just give you the formulas, and then you plug in numbers and see whether it matters or not. Okay, so that's the big picture. Now wait, I want to go from here to here. So suppose I have these sources, and each source has an exponentially distributed length of time with parameter gamma until he makes a request for service. That means that if any time I have a certain number of sources, then the time until the next request is made by those is the minimum of the think times, those exponential think times, of each of those sources. And the minimum of a bunch of exponentials is again exponential with a rate equal to the sum of the rates. So that means that I can use the same rate up equals rate down argument, arguing that when I'm in state j, the length of time until the next arrival, next request generated by one of these sources is going to be exponentially distributed with a parameter equal to the sum of the rates. And if there are j of them that are busy, there are n minus j that are available. So n minus j exponentials, each with parameter gamma, gives me an aggregate birth rate of n minus j times gamma. This is all in the book, of course. And this is one of the few books, if I can make a marketing pitch, where this model is actually considered in any detail. But I think it's becoming more important now than it used to be. Okay, so let me talk about that limit for a minute. So now we have a finite number of sources. Okay, so here is a source and a source and so on, and I got n of them. And they're going to make requests for service. So let's just look at these guys without regard to any servers and ask, what's the probability that in an interval of length j, of length x, I will make exactly j requests for service? So each of them has exponential think times. So the probability that any one of them makes a request for service in an interval of length x is going to be equal to 1 minus e to the minus gamma x. Okay, this is the distribution function of the think time for an individual source. By assumption, it's exponentially distributed. Now, we're going to remove that assumption, so this is one of the major points here. But right now, this is the probability then that this guy in the interval of length x will make a request for service. But they're all the same. We're going to assume that they each have the same parameter gamma. The sources are statistically identical to each other. So therefore, the probability that in the interval of length x, exactly j of them make request for service is this. That raised to the j power is the probability that j specific ones make a request for service, and 1 minus that, which is e to the minus gamma x to the n minus j, is the probability that the other n minus j guys do not make a request for service. So we're going to have exactly j request for service, and that has to be multiplied by the binomial coefficient, which tells the number of different ways I could choose the j guys who make requests for service out of the n guys who are eligible. So this is the binomial distribution. And now, let me erase this arrow here. As everybody knows, or if you don't know, take my word for it, it's easy enough to show. This is now a mathematics exercise. If I take the limit of this as n goes to infinity, number of sources goes to infinity, and the rate per source goes to 0. Remember, if I want to increase number of sources but keep the traffic the same, I'm going to make each source have less and less traffic but more and more sources. So I'm going to let the number of sources go to infinity, the rate per source go to 0, and keep the product, the number of sources times the rate per source, stay constant, which I'll call, let's see, did I give that a symbol? I'll call that lambda. This is the aggregate arrival rate, because it's the arrival rate per source times the number of sources. And now I take this limit, and now this is just arithmetic. It turns out to be given by the following. Lambda x to the j over j factorial e to the minus lambda x, which of course you recognize as the Poisson distribution. And this is just a standard idea from elementary probability that the limit of a binomial is the Poisson. Okay, so that means that if I imagine now that I have a queuing system in which, well, let's see, in this case I've said, it's implicit here, that each source in the interval of length x can make at most one request for service. But let me remove that, because I could say, well, yeah, but if I let n go to infinity so that the rate per source is going to 0, that means that the probability that any individual source would actually make a request for service is essentially 0, because I've got an infinite number of these sources, each of which is generating infinitesimally small traffic. So therefore, if I look at the queuing model that I obtain when I have a finite number of sources and then take the limit of the answer, I should get exactly the corresponding queuing model for Poisson input. So in fact, we'll see that when we take this model with block customers cleared, in the limit, you would get the Erlang B results. And if you take the case where the block customers are delayed, then in the limit, you would get the Erlang C results. So therefore, the Erlang B and Erlang C models are actually special cases of the finite, of the so-called quasi-random input. And for this reason, these are called finite source models, obviously because they're finite source. So finite source, that means quasi-random input. Although it doesn't have to. You know, this language grows up over 100 years by people working in different areas, some of whom are applied engineers, some of whom are mathematicians, and so of course terminology tends to diverge. But what that means also, this is the point I'm making, is that the case of infinite source, by this argument here, that corresponds to Poisson input. So typically, at least in some contexts, people talk about the Poisson input as being corresponding to infinite sources and quasi-random input as corresponding to finite sources. Now, the infinite versus finite, what that means is that if you have an infinite number of sources, then the calling population is not affected by removing a finite number of them and putting them in the queue or in service. Whereas if you have a finite number of sources, then when you remove some of them from being eligible to make requests for service, that means that the calling rate goes down because they're removed from the calling population. Question?
I assume it would be a slightly more complex situation if you had effectively not infinite source pool, but there's only, like, over time, the n fluctuates.
Okay, what happens if the number of sources itself is a random variable? Well, yeah, of course that makes things more complicated. And in principle, it might make things much more complicated because it depends on how they fluctuate. Because remember that these results all apply in equilibrium after the system has been in operation a long enough time for everything to settle out. So if in fact you don't have stable parameters during this time, then who knows what's going on. In fact, that's one of the questions about using the Poisson process to describe ordinary traffic. Because you could say, well, if you're looking at telephone traffic, for example, you could say, well, the calls may arrive according to a Poisson process, but the lambda should vary because certainly people get more calls, switching systems get more calls between 11 and 12 in the morning and 2 and 3 in the afternoon than 11 and 12 at night or 2 or 3 in the morning. So what do you do about that? And the answer from a practical point of view is, well, you consider what's called the busy hour, and you engineer your system for the busy hour under the assumption that during that hour things are stable, and that hour is short enough so that, long enough so that you can apply the equilibrium results. And then in the times when you are in the busy hour, the formulas are predicting well what happens. And when you're off the busy hour, the loads are actually less, and therefore you're giving better service than what your formulas had predicted. So if you design your system and engineer for the busy hour, you will do what you want during that time, and that is, do what you intended during that time, and you'll be better than that, giving better service during the times when the demand is low. Of course, nowadays, it seems that telephone systems do the reverse, which is they engineer for the time when nobody wants to use their systems, and they give great service in the middle of the night, but try and make a call during the day, and then your calls get dropped and everything screws up. Every time I make a phone call nowadays, I keep on saying to myself, I remember when you could only buy one color phone and you had no choice whatever, but it always worked perfectly. In fact, they used to engineer their telephones to have a lifetime of 40 years. And they would have a downtime in 40 years of a few seconds. And that actually worked. But the problem was that when you engineer something that's going to work for 40 years and then it becomes technically obsolete in one, then you have all this stuff that works great, but it doesn't have pictures and bells and whistles and all that. And so now we have systems in which you can have telephones do anything, but they don't work very well. So I prefer the old days. But that's just my personal predilection. Okay, so let's look at this quasi-random input from an intuitive point of view, get things going here. I'm going to start off and assume that I'm going to calculate the probabilities, what I'll call P1 of n and pi 1 of n. So I'm going to talk about a system with one server and n sources. And the p represents the fraction of time I'm in state 1, and the pi represents the fraction of sources that find the system in state 1 when it wants to use the system. So I've got one server, n sources. So here's my server, and here are my sources. So the p's and the pi's mean the same as before. The only difference in notation is I put the n as an argument. So the n represents a number of sources, whereas before number of sources was infinite or wasn't in there, wasn't specified. And I'm going to first consider the case in which n is equal to 1. Okay, so when n is equal to 1, what that means is I have one source and one server. Okay, so what happens? Let's say I start out with the source idle. The source is in the think state. And then he thinks a while, and then he makes a request for service. And on average, it takes him 1 over gamma in order to do that. I'm going to, remember this is intuitive, and I'm going to do everything in terms of average values. So on average, if his request rate is gamma, then 1 over gamma is the time until he makes a request for service. And when he makes a request for service, since I've got only one source and there's one server, the server must be available. So then he holds the server on average for a length of time tau. At the end of that time, he becomes idle. He reverts to his pre-request state, his think state, and then sometime later he makes a request for service, and the average time until that happens is 1 over gamma. Then he holds a server for a length of time tau, and so forth. So you get a diagram like this. Now, what's the probability that in this system with one source, the server is busy? I'm in state 1. So now I'll make the obviously correct intuitive argument and say, well, I've got these cycles, and the cycles are statistically identical, and so it ought to be true that the fraction of time that the server is busy, that's the fraction of time I'm in state 1, is the ratio of the average busy time per cycle, which is tau, divided by the average length of the cycle, which is 1 over gamma plus tau. So that should be my probability. This is a system that just goes off, on, and so forth. Now I'm going to multiply through by gamma. So I get gamma tau over 1 plus gamma tau. And then I'm going to define gamma tau as equal to what I call A hat. Because gamma tau is analogous to lambda tau, except that lambda is the rate aggregate for everybody, and gamma is the rate for a source when idle. Remember that a source now has 2 different arrival rates. When he's idle, when he's in his think state, the rate at which he requests service is gamma. And when he's busy, the rate at which he requests service is 0. Okay, so this A hat, I'm going to call that the offered load. It's analogous to A, per idle source. Okay, so there's a formula. This is the fraction of time the server is busy. A hat is the demand, the offered load, for an individual source when idle. And he has no demand when he's busy. What's pi? Anybody know? What's that? In this scenario, what's the numerical value for pi? 0. Because this is the conditional probability that the server is busy just before a source makes a request for service. But since there's only one source, that source can never find the server busy. And so therefore, the fraction of requests that are blocked is 0, but the fraction of time the server is in the blocking state is A hat over 1 plus A hat, which of course can be anything depending on the value of A hat. Now, what we did when we had Poisson input was we calculated the p's, and then we interpreted them as the pi's because of the pasta theorem, which said that the p's and the pi's are equal if we have Poisson input. But now we don't have Poisson input, so we can't do that. But we do have a formula. Let me write the formula. Let's see. I'll write the formula right here. Pi j is equal to lambda j pj divided by the sum of lambda k pk. summed over all k. We derived this formula earlier. Let me tell you where it is in the book. It's formula 2.6 on page 78. 2.6, page 78. And I said at the time I derived this using Bayes' rule that we would use it later, and we're getting to later. Now, if the lambdas do not depend on the subscript, then they cancel out. The denominator sums to 1. Pi j equals pj. That's pasta. But in our case, the lambdas are not constant. So this is a formula that we'll use later, but right now I'm not using the formula. Right now I'm just doing it intuitively. Okay, so the next case is let's take n is equal to 2. Okay, so now what does the diagram look like? Well, let's say we start out with both sources in the think state, which means that the time until the first request is the minimum of the think times of the two sources. So the minimum of the think times is exponentially distributed. It's the minimum of two exponentials. It's exponentially distributed with rate 2 gamma. So the average time until I make my first request is 1 over 2 times gamma. And then somebody makes a request for service. Okay, the server is held for a service time. On average, that's tau. And then becomes idle again. Now, what happens during the time that the server is busy? Now I have to make an assumption. Here, I didn't have to worry about what happened to the blocked customers because there were no blocked customers. But now, when the server is busy, the other source could make a request and be blocked. So I have to make an assumption. So now I'm going to assume, for the sake of simplicity, because this is just I'm just trying to illuminate things here. I'm going to assume that I have blocked customers cleared. So that means that in this model, if a source makes a request for service when the server is being held by the other source, then the blocked source simply reverts to his previous state and retries at a later time with the same parameter. So that means that any customer that arrives during here, at the end of this time, he's still going to be in his think state because he's going to revert to his think state. Then, when this guy finishes his service, we now have two sources that are idle. They have exponential think time, so it doesn't matter how long one has been idle in the past. It has no predictive value for the future. So the time until the next request for service is going to be, again, the minimum of those two exponentials, each with parameter gamma. So it's going to be 1 over 2 gamma. And so you're going to get a diagram just like before, except that the times between the think times are now going to have parameter 2 gamma instead of 1 gamma. Okay, so what is the P? What's the fraction of time that the system is in state 1, meaning the server is busy? Well, by the same argument, I'm going to say that these cycles are all statistically identical. So the probability that I'm in the state 1 should be the ratio per cycle of the amount of time I'm in state 1 to the total amount of the cycle. Yeah, question? This is a 2 here and a 2 here because I have two sources. What was that? Good point. Okay, two sources. I just did that to see if you were alert. So, good. Okay, what's the probability? It's the ratio of tau divided by 1 over 2 times gamma plus tau. If I multiply through by 2 gamma, I get 2 gamma tau over 1 plus 2 gamma tau, which is 2 a hat divided by 1 plus 2 a hat. Okay, so this is the probability with one source. That's the probability with two sources. What's pi? pi 1 of 2. What's the fraction of arrivals that are going to be blocked in a system with 2 sources and 1 server? Okay, now I want to make the same argument, same diagram, so I say the following. Well, now what I'm going to do is I'm going to take the ratio of the number of customers who were blocked per cycle to the number of requests made per cycle. That's what we did for example, in homework 1. That's the frequency version of this conditional probability. It's what the arrivals see. So to find the probability that an arrival finds a system in the blocking state, I count the ratio of the number who find the blocking state to the total number offered. Same thing we did in homework number 1. Okay, so how many customers are going to be blocked in this system? Well, what happens is when the first customer, the first subscriber, makes his request for service and enters service, the other subscriber is still in his think state. He's making a request at rate gamma. The length of time that the server is busy is tau. So the average number of requests made by the guy who is not using the server is gamma times tau. Okay, that's the request rate when idle times the average time. Okay, that's the number of requests that find the system in state 1 in a cycle. Now, how many requests are made in a cycle? Well, let's see. How many requests are made during the blocking part of the state? Well, we already know that, gamma tau. How many requests are made during the think part of the cycle? Exactly 1, namely the one that makes the server busy. So what's that? Well, that's equal to a hat over 1 plus a hat. Okay, so now the question is, does anybody notice anything here? Is there anything worth remarking about what I just found? Well, looks to me like that and that are the same thing. In other words, pi 1 of 2 is equal to p1 of 1. So is that just a, let's see, where should I write that? Okay, I'll get rid of this formula here. We don't need it at the moment. My observation is that the probability in a 2-source system that a request finds a server busy is the same as the probability in a 1-source system that the server is busy. Okay, we got that because we made these calculations and they turn out to be the same thing. So I can give that an interpretation. I'd like to say, well, I want to calculate these p's and these pi's. The p's I know how to calculate because they come out of rate up equals rate down. Previously, I said the pi's are the same as the p's because of pasta, but now I don't have pasta. But now I can say, well, wait a minute. We have 2 sources here, and apparently the probabilities as seen by the source in a 2-source system are just the same as if he was not a part of the system and observed the 1-source system that would exist without him. In other words, I'm going to remove the particular guy from consideration and make believe that he plays the role of an observer of the same system, except with him not a member of it. Now, that's not right, because that ignores the fact that when this particular guy makes his request for service, he changes the state of the system. So he's not an outside observer. He interacts with the system and causes its states. But this result seems to say that, at least for this case, the probability of finding the system in state J if there are n sources is the same as the probability of being in state J if there were n minus 1 sources. In other words, it says that what the arriving customer sees in an n-source system is just what he would see if he were not part of that system, but observed the same system with him missing and n minus 1 other sources. Yeah.
That's because you're using a block called clear. Because effectively when he bounces, it doesn't actually change the system.
Good point. Okay. Why did this work? There's actually two reasons it worked. One is because there's only one server. The other is because I had block calls cleared. But suppose I have more than one server and don't have block calls cleared. Then what? You could still make the argument that it seems to be a reasonable approximation. Let's say you're an engineer, and this is pre-queuing theory days, and you're trying to solve this problem. And you say, well, I don't know what's going on, but I'll just say that if I have a whole bunch of sources on a bunch of servers, I'll just make believe that one of them is removed and plays the role of the outside observer of the system consisting of everybody else. And that should be approximately right. And the answer is, yeah, not only is it approximately right, it's exactly right. And we're going to prove this is true in general for any Q discipline and any number of servers. So that's why this is an interesting model. But there's something that's even more important as to why it's an important model. And that is that when I made this analysis, I had to assume that I had exponential think times and exponential service times. Now we already know that if we have block customers cleared and we have Poisson input, then we don't have to have exponential service times. But we still have to have exponential interarrival times. However, it'll turn out in this model that this result is correct. In fact, all of these results are correct even if I don't have exponential think times. In other words, this model is totally independent of any probability assumptions. It's really incredible. That means that it's very robust because in cases where it might apply, it doesn't make any difference what the underlying distributions are. So what we'll do is we will generate the theory assuming everything is exponential, because that's the sufficient conditions for rate up equals rate down. We'll get the formulas, then we'll write a simulation, then we'll compare the simulation with the formulas for the case of exponential think times and exponential service times. And of course, everything is going to work. Then you're going to run the same simulation, except you're going to make the think times exponential and the service times constant, and you're going to make the service times exponential and the think times constant, and you'll find it doesn't make any difference. You get the same answers. Okay, so we have 1 minute and 35 seconds, 34, 33, 30. Any questions before we quit here? So I'm going to go back to this next time, and this will be homework number 4. So the homeworks are going to start to be coming faster now, but actually each homework is only a small change from the previous one. I'll give you the theory, it's just formulas, and then for the simulation, what you have to do is you have to go back to homework 1, and you have to change the input from Poisson input to Kwazii random input. So that's a couple of instructions, and then everything else carries over. Okay, so I'll see you all Monday.